Hi everyone. This lecture series, lecture 14, considers loads and container parallel for systems. So here we go. Types of loads and their calculations. Loads are generated due to the weights of the structural members, the occupants occupying the or using the structure, machines, and heavy equipment. Wind loads, earthquake loads, blasting loads, earth pressure, water pressure, etc. For a heavy equipment over a small area, the equivalent load may be represented as a force, which is equal to the weight acting over a point. These loads are called point loads or concentrated loads. For members that are prismatic or identical, members spaced equally apart, carrying identical floor loads in a form of pressure, the equivalent load may be represented as line loads after multiplying the pressure by the constant spacing. An example of this is the weight of a beam itself plus the uniform loads from the floors. For walls carrying varying pressure caused by wind, earth, and water or fluid pressure normal to the large area, the loads are represented by surface loads. So here is the example of point loads or concentrated loads acting on a beam. This is an example of line loads applied over a beam. And another way to represent this surface load is this one, represented by an area. So this is an example of surface loads. We have this system here where it is subjected to the walls are subjected to wind pressure, the roof, and the leeward roof also subjected to surface loading. So let's have the general expression for line loads. So consider these line loads and it varies with the length. So the function or the load, the intensity of the load is denoted by this function of x in Newton per meter or kilonewton per meter, or it may be in pounds per foot. Let's consider a strip whose height is equal to W and the thickness is dx. And its centroid of this differential strip is located at distance x from the left end. So this the total area of this line load diagram is equal to the force F, and it is located at its centroid of that area. So let's call that F, and this area of strip is the differential of that force F. So this differential force is simply equal to the area of the strip, which is W times dx. So integrating, take note that we also define this W dx as the differential area of that strip. And integrating both sides, then we have f equals the integral of W dx, or simply the area of this line load diagram. So if we are familiar with this different geometric areas, it may be a rectangle, a triangle, or trapezoid, or second degree loading, then we can easily compute the equivalent force acting at the centroid of that area. Thus, the equivalent force of, of the line diagram is simply equal to the area of the diagram. Now, to locate this equivalent load or force, we apply the Varignon's theorem for areas instead, or for force. So F, F times part x, the moment of the resultant force, which is F times part x about this left end here, is equal to the sum of the moments of its components. And one component is represented by df, and its distance from the left end is x. So F is equal to the area, remember, and df is equal to wdx, then times this x here. So this summation is replaced by the elongated s, or the integral sign. So we have part x equals integral of x df over f. And since f is simply equal to the area under the line load diagram, then we have integral area times var x equals integral of x dA. So var x is equal to integral of x df over f, or integral of x dA over a. So the equivalent load or force is located at the centroid of the area. So in general, if the line load has the equation w equals kx to the n, where n is the degree of the curve such as 0, 1, 2, etc., when x is equal to b, with w equals h or wo, then this is the curve, this is the expression. Then we simply obtain the area of this curve in general. So we have here the height is w at any point, and the thickness is dx. So differential force is acting through the centroid of that state, and let us say this is the centroid of the entire area. So this is x, and part x from the centroid of the entire area. Call that part x1. And let's call this part x. So distance from centroid of the entire area from the vertical leg. So w equals h equals kb to the n from this equation, when x is b, so that k is h over b to the n. So w therefore is h over b to the n times k times x to the n. So we have area for df. So this is w, h over b to the n, x to the n. So force therefore equals integral from 0 to b of k x to the n dx, or this expression here where k is h over b to the n dx. So h over b to the n is constant, so we can easily evaluate the integral of x to the n dx. It is x to the n plus 1 over n plus 1. So h over b to the n, x to the n plus 1 over n plus 1 from 0 to b. Substituting the value of b, so h over b to the n, then b to the n plus 1 over n plus 1 minus 0. Lower limit is 0. So we break b to the n plus 1 into b to the n times b, so that we can cancel b to the n. Then cancelling out b to the n, then we have the expression for the force, which is the area under the load diagram. It is equal to dh divided by n plus 1. So remember this is the area, dh over n plus 1, where n is the degree of the curve. So if n is 0, then this is a horizontal line, and it is a rectangle, so it is just dh. If n is 1, then it becomes first degree, so this is our triangle, so it is dh over 2, the area of the triangle, and so on and so forth. So by Varignon's theorem, f times bar x1 equals integral from 0 to b of, this is the moment of its component, differential force times x. So replacing the value of f and its differential f, which is h over b to the n, x to the n dx times x, and we cancel out h and combine like terms. So we have to cross multiply n plus 1 over b to the n times b is b to the n plus 1. Then we have integral of x to the n times x is x to the n plus 1 dx. Evaluating this by power formula, we have n plus 1 over b to the n plus 1, x to the n plus 2 over n plus 2. So part x1 is n plus 1 over b to the n plus 1, x to the n plus 2 over n plus 2, 0 to b. Substituting the value of b and noting that b to the n plus 2 divided by b to the n plus 1 is just b. So part x1 is n plus 1 over n plus 2. b to the n plus 1 over b to times b to the n plus 2 over n plus 2. So take note that this b to the n plus 2 over b to the n plus 1 is just b. So part x1 is n plus 1 over n plus 2 times b. So that's the distance from this 0 end to the centroid of the area. But part x, we compute part x, the more important formula. It is b minus bar x1. So cross multiply and simplify. So we have bn plus 2b bar x is bn plus 2b minus bn minus b over n plus 2. So cancelling out bn, 2b minus b is b. So bar x is simply b over n plus 2. So if the area is bh over n plus 1, bar x is b over n plus 2. Take note that bar x is the distance from the centroid of the area to the vertical length or W. That's it. So for n is 0, let's check. It is a rectangle. And of course, bar x would be bh over 0 plus 1. So area is bh, f is bh, or simply the area of the rectangle. In this case, the base is L, the intensity of the load W, so WL, and the distance from centroid from the right is L over 2. For n is 1, then the force is W times L divided by 1 plus 1, so it is a triangle, so WL over 2, the force, and the location of centroid from the right is L over 3, so L over 1 plus 2. If n is 2, it is a spandrel of parabola or complementary parabola. So the force is WL here divided by 2 plus 1, so WL over 3. And the distance from the right would be L over 2 plus 2, so L over 4. So it is a second degree parabola. So for various cases, use integration. So general expression for surface loads. So we have here the surface loading, and we have here the force. In general, let's call that F. And let's consider its component, differential element. We have differential area constant, then the height is the intensity of pressure P. So therefore, the differential force is simply equal to the area and the product of area and pressure. So it's just the volume of this prismatic differential element. So that's differential force, which is equal to pressure times dA. So F equals, or dF equals pressure times dA. So the location of the force is denoted by bar X and bar Z, assuming the area lies on the XZ plane. So this distance is bar Z or Z sub G or Z bar. So from differential force equals dV or differential volume from the figure, because dA times intensity of pressure, the height is differential volume, equals pressure times dA, integrating both sides. So we have dF, integral of dF equals integral of dV equals integral of dVA. So F therefore equals integral of differential volume or simply integral of dVA. So this is the general expression for F, integral of dVA. Unless otherwise, the intensity of pressure is uniform, then it becomes pressure times area. So area times the height, intensity of pressure, it is geometrically interpreted as volume of the surface. So if P is uniform, then F is PA. So take note that F is equal to the volume or pressure times PA for uniform P. If not, then F is equal to the integral of dVA. So these are the common surface loads. So if we have a uniform P, and these are the dimensions, then F is simply PAB because or pressure times AB. So F equals PAB, and it is located at A over 2 and B over 2. Then for this uh, surface load uniform, but the area is triangular. So that's the location of the centroid. This time it is area of the triangle 1/2 AB times pressure. So PAB over 2. That's the force, and it's located at A over 3 and B over 3 from that side. Then for this general pressure diagram with varying intensity, so let's say P1 and this is P sub 2, where P2 is greater than P1 and the height is H. This is over a rectangular vertical area. Then we divide that into two parts. So we have a uniform pressure diagram, and this one is linearly varying uh, pressure intensity. So we have rectangular and triangular. So for the rectangular, we'll call the force as F rectangular, and for the triangular, F triangular. Now, F rectangular is simply equal to the volume of the prism or this rectangular parallelepiped. So it is equal to P1 times BH F rectangle. So if this is the projected area of this rectangle here, then the dimensions BH. So F rectangle is acting as the centroid of this rectangular area. That's the centroid of the rectangular area. It is where F rectangle acts. Then the distance would be, this is A over B over 2 and H over 2. Then for the triangular portion, it acts below the GR and it acts H over 3 from the bottom. So that's the centroid. It is where the F triangular force passes through, and the distance is B over 2 from the left and H over 3 from the bottom. Then for the total force, call that F. So F rectangular is P1BH, F triangular is quantity 1/2 quantity P2 minus P1 BH. So 1/2 P2 minus P1 BH. Then for the general force, the total force, it is F rectangle plus F triangle. It acts somewhere between GR and GT. So F is F rectangle plus F triangle. Then it acts somewhere between GR and GT. So each location is B over 2 from the left, but let's call it HF from the bottom. So HF is determined by Varignon's theorem. So F, which is F rectangle, F triangle, times HF equals F of rectangle times H over 2 plus F of triangle times H over 3. And we can locate HF from the bottom. So that's it. Okay, let's have this example 14.1. For the line and point loading shown applied on the beam, calculate the magnitude of the resultant force and its location from point A. So first, let's divide the line loads into known areas. So we have two triangles and three triangles all in all. So let's denote the force equivalent to the area of this triangle as F1, for this triangle as F2. Now this distance is 1/3 of 3.6, so that's 1.2. So F1 is 1/2 of 3.6 times 12. So therefore, area or F1 is 21.6. For F2, its distance from the left is 2/3 of 3.6. So that's 2.4. And F2 is the area of this triangle, 1/2 of 3.6 times 36. Distance of the 40 kilonewton load is 2.4 plus 2.6, so that's 6 meters. And F3, the distance from this point is 1/3 of 5.4 is 1.8 plus 3.6. So distance of F3 from the left end A is 5.4. So F2 is area of triangle 1/2 of 3.6 times 36, so 64.8 kilonewtons. So this distance is 1/3 of 5.4, 1.8 plus 3.6, so 5.4. F3 is 1/2 of 5.4 times 36, so it is 97.2 kilonewtons. And of course, our F4 is that 40 kilonewtons. So the resultant may be located somewhere here, and its distance from the left, let's call it X sub A. So therefore, the resultant is the sum of these forces. Let's consider downward as positive because all forces are downward. So R is equal to 223.6 kilonewtons downward. Then we apply Varignon's theorem to locate that single resultant force from the left. So that is R times XA, or 223.6 times XA, is equal to F1, 21.6 times 1.2, plus F2, 64.8 times 2.4, plus F3, 97.2 times 5.4, then lastly plus 40 times 6. Solving for XA, XA is 4.232 meters. So we have answered the question in problem 14.1. So we say that the resultant is 223.6 kilonewtons downward and is 4.232 meters to the right of support A. So let's have example 14.2. The loadings on a beam are shown in the figure. Compute the resultant force of the system and specify its line of action with respect to the left end of the beam. The 40 kilonewton load is at the midspan. So first, let's divide the areas into known areas. So we have here area of triangle F1. Its distance from the left is 2/3 of 3, so 2 meters. And F1 is equal to 1/2 of 3 times 30, so it is equal to 45 kilonewtons. Next, we divide the trapezoidal line load into two triangles, and let's call this F2, and its distance from the left is 1/3 of 3 is 1 plus 3, so 4 meters. So F2 is 1/2 of 3 times 30, so it is also equal to 45 kilonewtons. F3, the area of this triangle, so its distance from the left is 2/3 of 3 is 2, this is 2, plus 3, so 5 meters from the left. F3 is 1/2 of 3 times 18, so it is equal to 27 kilonewtons. Then F4, this spandrel of parabola, its location is, because this distance is 4 divided by second degree plus 2, so 4 over 4 is 1. 1 plus 6 is 7 meters from the left end. So F4 is equal to 1/3 of 4 times 18, so it is equal to uh, 24 kilonewtons. Then the 40 kilonewton load acts at a deep span, so its distance from the left end is 5 meters. And take note that we also have 120 kilonewton clockwise couple. So the resultant is downward, and let's treat downward as positive. Its location from the left end, let's call that x sub r. So r is 45 plus 45 plus 27 plus 24 plus 40. So the resultant is 181 kilonewtons downward. Then we apply Varigton's theorem to locate its position from the left end. So clockwise moment of the resultant is also equal to the clockwise moments of its components. So 181 times xr equals f1 45 times 2 plus f2 45 moment arm 4 plus f3 27 times 5 plus f4 24 times 7 plus 40 times 5, then plus this clockwise couple of 120 kilonewton meter. So solving for xr is 4.934 meters. So therefore, the resultant is downward 181 kilonewtons and is acting at 4.934 meters horizontally from the left end. Or the resultant is 4.934 meters to the right of the left support. So let's have this example 14.3. Determine the single force that is equivalent to the loads acting on the cantilever beam. Specify the point of application of this resultant on the beam. So this is the given cantilever beam. Obviously, the resultant is a downward force of 400 newtons. So the resultant may be located somewhere between the 200 newton forces. And we'll call its position from the fixed wall as x sub w. So R is 400 newtons downward, obviously 200 plus 200. Then we use Varignon's theorem to locate it from the fixed wall. So the moment of the resultant about the fixed wall is counterclockwise. So all these are counterclockwise except the couple. So 400 times xw equals 200 times 0.4 plus 200 times 0.6 minus 100. So x sub w equals 0.45 meters. So we say that the resultant is 400 newtons downward, acting 0.45 meters from the fixed wall, or to the left of the fixed wall. Then, example 14.4, so that the resultant force in the system shown below can be applied at point B, what should be the couple acting horizontally at A and at B. So this is the given system. Then this system is equivalent to resultant which acts at B, and the resultant is the resultant force is a downward force. Then the couple would be 90 times 1.8 counterclockwise minus 30 times 0.45. So the net couple is counterclockwise. So first, let's solve for the resultant. Let's consider downward as positive because the downward forces are greater than the upward force. So R is 90 plus 30 minus 45. So R is 75 newtons. Let's transmit that at D. But before that, let's compute the moment of the system about D. So moment about D is 90 times 1.8 minus 30 times 0.45. So the moment about D is 148.5 Newton meter counterclockwise. So that the couple, the forces of the couple will be counterclockwise. So the force at D should be to the left and the force at A should be to the right. So that should be the direction of the horizontal forces, the forces of the couple, so that the resulting couple is counterclockwise. So since the distance is 0.9, so HA times 0.9 is equated to 148.5. So HA times 0.9 is equal to 148.5. So HA is equal to HD equals 165 newtons. So we say that the resultant is 75 Newton meter acting at the vertical downward, and the forces would be HA equals 165 newtons rightward and 165 newtons at the leftward. So that's it. So example 14.5, find the value of F and Q so that the four forces shown below produce a downward force of 750 newtons acting 8.2 meters from the right end of the bar. So this is the given figure, and this is equivalent to this system here, a downward force of 750 newtons acting 8.2 meters from the right end of the bar. So first, summation forces y equals 750, considering downward forces as positive because the resultant is a downward force. So 750 equals F minus Q plus 600 minus 200. So F minus Q therefore equals 350. Call that equation 1. For the second equation, we sum up moment about the right end and we consider counterclockwise as positive. And we equate the moment to 750 times 8.2. So C sub R is 750 times 8.2 counterclockwise. Then it is equal to, this is counterclockwise, F times 9, the sum of the moments of its components. So this is clockwise for Q, so minus Q times 5, then plus 600 times 2, and of course the 200 Newton force as the moment. So second equation, 9F minus 5Q equals 4,950. So substituting the value of Q, which is F minus 350, into equation 2, or solving the two equations simultaneously, the values of F and Q are, F is 800 newtons downward and Q is 450 newtons upward. So you just solve these two equations simultaneously. You may substitute Q equals F minus 350 into equation 2 and you arrive with these answers. Example 14.6, for the point loads shown acting on the pink truss, determine the amount and the position of the resultant from point A when the angle theta is 40 degrees. Since the pink truss is symmetrical and the loadings above on the top chord joints are symmetrically loaded, so the value of theta does not matter. So these upper downward loadings can be represented by a single force acting at the center portion, same as the point of application of 1400. So we will call that R1 or RT, R of the top chord forces. So R sub T is 500 times 2. By the way, its distance is half of the span, 13.5 divided by 2, so 6.75. So R sub T is 500 times 2 plus 1,200 times 2 plus 1,400. So R sub T is equal to 4,800 newtons also downward. Then, therefore, the resultant is equal to 4,800. So let us say that's the location, and its location from A is denoted by X sub R from the left end. So the resultant, let's consider downward positive, is 4,800 plus 4,000 plus 6,000. So that would be 14,800 newtons downward. And to locate it, we use Varignon's theorem. We sum up moment about the left end. Then it is equal to the sum of the moments of its components. So 14,800 XR equals RT, 4,800, its distance is 6.75, plus 4,000 times 4.5, then plus 6,000 times 9. So solving for X sub R equals 7.054 meters. So we say that The resultant of these forces on the fin thrust is equal to 14,800 newtons downward, acting 7.054 meters to the right of the left support, or from the left support. So that's it. So let's have example 14.7. If the resultant of the system is a downward force of magnitude 1,200 newtons acting 3.6 meters to the right of A, determine the magnitude of the uniform load W and the magnitude of T. So this is the figure, this is the given system. So this is equivalent to a force of 1,200 downward acting 3.6 to the right of point A. So this is 3.6. So first, for the resultant force, considering downward as positive, because the resultant is downward, we have F1, which is equal to the area of this triangle, rectangle 4.8 W located 2.4 from point A. Meters F2 is area of this triangle 1/2 of 3 times W. This is 1/3 of 3, 1 plus 4.8, so 5.8 from the left point or from the left end A. So first R1, F1, area of the rectangle, so 4.8 times W. F2 is 1/2 of 3 times W, so it is 1.5 W. Then R, which is 1,200 downward, must be equal to 4.8 W plus 1.5 W minus P, because P is upward and we consider downward as positive. So simplifying, this is 6.3 W minus P equals 1,200, equation 1. Then for the second situation, because R and its position is located, so we consider moment of the resultant, in this case clockwise, as the sum of the moments of its components, and we consider clockwise positive. So 1,200 times 3.6 equals 4.8 W times 2.4 plus 1.5 W times 1.5.8 and minus P times 2. So simplifying this equation, we have 20.22 W minus 2P equals 4,320. From equation 1, we substitute P equals 6.3 W minus 1,200 into equation 2. So we can now solve W. W is equal to 252 Newton per meter. Then substitute in equation 1 to solve for P. Minus P equals 1,200. So solving for P is 387.6 Newtons upward. So therefore, the magnitude W is 252 Newton meter and P is 387.6 Newtons upward. That's it. So example 14.8, for the loadings shown on the beam, determine the resultant force due to the loads and its location from point B. So that's the figure. So let's have our solution. So first, let's divide the line loadings into known areas. So we have triangle, and let's divide this into the trapezoid into triangle and rectangle. The intensity of the load, this one is 24, 48 minus 24, and for the rectangle, it's 24 kilonewton per meter. So we will call this F1. Its distance from the left is 2/3 of 2.4, so 1.6, because that's 0.8. So 1.6 from a 0.8 meter from B. So we should reckon it from B, because the question here is location of the resultant of the loads from B. Then this one is F2. Its distance from the left from point B is 1/3 of 10 plus 1.5, 1/3 of 11.5, and that is 23/6 meters. Then F3, this rectangle here, its location from B is 11.5 divided by 2, 5.75. And of course, this 20 is a concentrated load. So F1 is 1/2 of 2.4 times 48, so 57.6 kilonewtons. F2 is 1 half of 11.5 times 24. So F2 is 138 kilonewtons. F3 is 11.5 times 24. So it is 276 kilonewtons. So R therefore is the sum of these forces plus 20 considering downward positive. So let us say that's the position of R and its distance from B as XB. So R is 57.6 plus 138 plus 276 plus 20. So the resultant force is 491.6 kilonewtons downward. Then we use Varignon's theorem to locate that signal force R. So 491.6 times xb, that's clockwise. And since the moment of F1 from B is counterclockwise, so it's negative 7.6 times zero point 0.8. F2 is positive, so plus 138 times 23 over 6 plus F3, which is 276 times 5.75, then minus 20 times 2.4. So solving for x sub b is 4.113 meters and R is 491.6 kilonewtons. So therefore, the resultant is 491.6 kilonewtons downward and x sub b, or it is acting 4.113 meters to the right of point B. So let's have now this example 14.9 about surface loadings. So the rectangular footing shown is 2.5 meters into the plane of the figure, and is subjected to the soil pressure shown. Determine the load it carries in kilonewtons and its location from the left edge. So that's the given figure. Take note that this pressure here is in kilopascals. To convert them into kilonewton per meter, we simply multiply it by the dimension perpendicular to the plane of this figure, which is 2.5. So 8 times 2.5 would become 20 kilonewton per meter. 14.4 times 2.5 would become 36 kilonewton per meter. 21.6 times 2.5 would become 54 kilonewton per meter, and 8 kilopascals times 2.5 will be 20 kilonewton per meter. So next, we divide the loading, this trapezoid here, into two triangles like that. And for this trapezoid here into two triangles, this triangle and this triangle here. And this one, this trapezoid here as two triangles again in that manner. So let's call this force F1, and its location is from the left edge is 1/3 of 0.6, so 0.2. Then F2 is this triangle here. Then 2/3 of 0.6 is 0.4 from the left edge. Then this is rectangular, so it is located, let's call it F3, it is located 0.6 plus half of 1.5 is 1.35 from the left end. And F4 would be this triangle here. Then it is located 0.6 plus 1.5 is 2.1 plus 1/3 of 1.8, 0.6, so 2.7 from the left end. Then F4, this triangle here. F5, this triangle here. It is located 2.1 plus 2/3 of 1.8, which is 1.2. So 2.1 plus 1.2, 3.3 meters from the left edge. Then F4 would be this bigger triangle, and its distance from the left edge is 2.1 plus 1.8 is 3.9 plus 1/3 of 0.5. So 3.9 plus 1/3 of 0.5 is 61 over 15. And lastly, F7, its distance from the left end is 2.1 plus 3.9, 4.4. 4.4 minus 1/3 of 0.5. So 127 over 30. So since we have reduced the surface loading into 9 loads, then we simply compute this magnitude of these forces as area of triangle. So the resultant would be here, but take note, we are not looking for the resultant, we're looking for the load it carries. So it's the opposite of the resultant, so it's downward, but they are collinear for equilibrium purposes. So let's call that as LD, and its location from the left end is also the location of the resultant of this soil pressure from the left end, so X sub R. So F1 equals 1 half of 0.6 times 20, that would be 6 kilonewtons. F2 is 1 half of zero point 0.6 times 36 is equal to 10.8 kilonewtons. F3 is 1.5 times 36. It is equal to 54 kilonewtons. F sub 4 is 1 half of 1.8 times 36. It's 32.4 kilonewtons. F sub 5 is 1 half of 1.8 times 54. So it is equal to 48.6 kilonewtons. F sub 6 is this triangle here, 1 half of zero point 0.5 times 54. So it is equal to 13.5 kilonewtons. Then finally, F7 is 1 half of zero point 0.5 times 20. So it is equal to 5 kilonewtons. So the resultant is an upward force, and it is equal to the sum of these forces. So adding these forces, resultant is 170.3 kilonewtons upward. But the loading is downward. The, the load on the footing is equal to this upward force. So LD is 170.3 kilonewtons. Then for its location, we equate the moment of the resultant about the left edge to the sum of moments of its components. So it is equal to 173.3 times XR counterclockwise. So all of these are counterclockwise. So equals F1 times 0.2 plus F2 10.8 times 0.4 plus F3 equals 54 times 1.35 plus F4 32.4 times 2.7 plus F5 48.6 times 3.3 plus F sub 6 13.5 times 61 over 15, and plus F7 5 times 127 over 30. So solving for XR is equal to 2.363 meters. So we say that the load is 170.3 kilonewtons downward, and it is located at 2.363 meters to the right of the left edge. So let's have example 14.10, the second example for surface loadings. One phase of the building is subjected to a wind pressure that varies linearly from 2 kilopascals at the bottom to 5.2 kilopascals at the top. So determine the resultant wind force and its location relative to the bottom left corner. So this is the phase, and the wind is projected perpendicular to that phase, and the pressure varies from 2 kilopascals to 5.2 kilopascals. So let's draw the pictorial view. So let's divide the areas into two, and there are four types of forces acting on each area, and they are collinear with the vertical line through the center of each area. So this is the wind pressure. So we have 2 kilopascals at the bottom to 5.2 kilopascals at the top, but we don't know yet the pressure at this level here. So we apply similar triangles. We have, let's call that the total pressure as P. So this is P minus uh, P minus 2 as to 45 equals 5.2 5.2 minus 2 as to the total height is 75 meters. So 75. So P minus 2 as to 45 equals 5.2 minus 2 as to 75. Solving for P at this level here, it is 3.92 kilopascals. So for this is the center line, vertical center line, the centroid of the two forces for rectangular and triangular are on this vertical line. And this is the vertical line, the forces acting on this left portion of this rectangle are collinear. And it is 10 meters from the left. The second one is 20 plus half of 15, 27.5 meters from the left. So for F rectangle 1, so it is 2 kilopascals times area. And the area is 20 meters by 45 meters. And each centroid, or it passes through half of 45 on this line here. So 10 meters to the right, and from this corner 10 meters to the right, and half of 45, 22.5 meters above the bottom. So point A is, of course, obviously 10 meters to the right of this corner and 22.5 or half of 45 above the bottom. Then for the triangular part, because this is trapezoidal, it is, we will call that F triangle 1, and it is above because it's 2/3 of 45, so 30 meters above above point A. Let's call that point B. So it is 2/3 of 45, so 30 meters, and it is vertically aligned. Then for F rectangle 2, for this rectangular area here where the pressure is 2 kilopascals uniform, it is acting at this on this line, and it is 27.5 from the bottom left corner because this is already 20 plus 15 over 2, and above, because the height is 30 is 45 plus 30, 75, so 37.5 meters above the bottom. So point C is 27.5 from the bottom left corner and 37.5 above the bottom. That's 27.5 and that's 37.5. And finally, F triangle 2, which is above somewhere here. Let's call the point of intersection with the wall as D. Then it is acting 27.5 horizontally from this bottom left corner and 2/3 of 75 or 50 meters above the bottom. So 50 is 2/3 of 75 because that's triangular. So let's compute FR1. It is simply the volume of rectangular parallelepiped, which is 2 kilopascals, the pressure, then the area 20 times 45. So 2 kilonewtons per square meter, the area is 45 times 20 or 20 times 45. So FR1 is 1,800 kilonewtons. F triangle 1 is 1/2 of P minus 2. So 1/2 of P minus 2, then times the area 45 times 20. So 1/2 of P minus 2 times area 45 times 20. So F triangle 1 is 864 kilonewtons. Then F rectangle 2 is simply 2 kilopascals times the area of this space is 15 by 75. So 2 kilopascals times 15 times 75 or 75 times 15. FR2 is 250 kilonewtons. Then F triangle 2 is 1/2 of 5.2 minus 2 times area 15 times 75 or 75 times 15. So F triangle 2 equals 1,800 kilonewtons. So the resultant, we will call that resultant R, and its point of intersection with the wall is at E. So E is somewhere here. We will call its distance from the left as X sub E and its distance from the bottom as Y sub E, as shown in the figure. So R is the sum of the forces, uh, 1,800, 864 plus 2,250 plus 1,800. So R is 6,714 kilonewtons, and its direction is perpendicular to the face of this side of the building, and its location by Varignon's theorem. So we have R 6714 times XE equals 1,800 times 10 plus 864 times 10 plus 2250 times 27.5 plus 1,800 times 27.5. So solving for x sub e is 20.56 meters. Then Varignon's theorem, we sum up moment about the bottom through O. So we have 6714 times YE equals 1,800 times 22.5 plus 864 times 30 plus 1,000 plus 2,250 times 37.5, then plus 1,800 times 50, two-thirds of 75 is 50. So solving for YE is 35.86 meters. So therefore, our answer R is 6714 kilonewtons perpendicular to the face of that building, and it is located at the point from the bottom left corner, which have coordinates of XE 20.56 meters right of and 35.86 meters above the bottom left corner. So that's the final answer. And finally, this is our last example. 14.11, a rectangular closed tank has a square base 1.5 meters on a side. The height of the tank is 3.6 meters. It contains molasses, specific gravity 1.5, and 1.8 meters thick, water 1.2 meters thick, and the remaining space is air that is under a pressure of 21.74 kilopascals. A gauge attached at the bottom of the tank reads 60 kilopascals. So the pressure at the bottom of the tank should be 60 kilopascals. So determine the following: the total pressure or the force on one side of the tank and the location of this force from the bottom of the tank. So this is the figure. Then let's have it divided, the area, into the following. So P1 is pressure in the airspace, 21.74. Then P2 is pressure at the top plus specific weight of water, which is 9.81 times the depth, 1.2. So we will call this force equal to the volume of this rectangular parallelepiped. This is rectangular parallelepiped because the tank has a square bottom, square base, so 1.5 meter, then perpendicular to the board, perpendicular to this plane is also 1.5. So therefore, you just extrude this, then it is a rectangular parallelepiped, 1.5 meters perpendicular to this plane of the figure. So F1, then this triangle here as F2, then this rectangle here, that one, small rectangle here as F3, and the remaining triangle face here, but that's a triangular wedge actually, uh, F sub 4. So take note that these forces are equal to the volume of the pressure diagram. So before that, let's solve for P2. So P sub 2 is P1, 21.74 plus, because this is water, plus 9.81 times 1.2. So from P6, it is gamma times depth. 33.514 kilopascal. So P3 is 60. To prove that this is 60, it is equal to P2 plus specific weight of molasses, which is specific gravity times 9.81 times thickness 1.8. So P3 is 33.512 plus 1.5, 9.81 times 1.8. So that's 60 kilopascals. So let's now solve F1 as volume of this rectangular parallelepiped. So it is P1 times height 3.6 times perpendicular to the board 1.5. So height, base 21.74, then 1.5 perpendicular to the board times height 3.6. Or pressure times area where that pressure is acting. So it is equal to 117.4 kilonewtons. F2 is 1 half of P2 minus P1 times 1.2 times 1.5. So 1 half is 0.5, then P2 minus P1 times 1.2 times 1.5 perpendicular to the board. So F2 is 10.595 kilonewtons. F3 is area volume of this rectangular parallelepiped, and its volume is P2 minus P1, that's the horizontal, times height 1.8 times perpendicular to the board 1.5. So 33.512 minus P1 times 1.8 times 1.5, 31.784 kilonewtons. F4 is 1 half of P3 minus P2 times 1.8 times 1.5. So 1 half of P3 minus P2, 1.8, 1.5, 35.759 kilonewtons. So next, we locate the resultant. So it is somewhere there. Its location from the bottom is called that H sub B. Then H sub 1 is, because this is rectangular, so half of 3.6 is 1.8, H sub 1. By the way, R is equal to the sum of these forces. It is equal to 195.5 kilonewtons rightward or perpendicular to that area on the right side. Then H1 is 1.8. H2, the location of F2 is 1.8 plus 1/3. This is 1/3 of 1.2, which is 0.4. So 1.8 plus 0.4, 2.2 meters. Location of F3 is, this is a rectangle, so half of 1.8, 0.9 each day. And H4, the location of F4 from the bottom is 1/3 of 1.8, so 0.6. So let's apply Varignon's theorem here to locate R. 195.5 times HB equals F1 times 1.8 plus F2 10.595 times 2.2 plus F3 31.784 times 0.9 H3 plus F4 35.759 times 0.6. So solving for H sub B, it is equal to 1.456 meters. So therefore, we say that the resultant force is equal to 195.5 kilonewtons acting rightward, perpendicular to the plane of that side, and 1.456 meters above the bottom. So that's the way how to state the answer. Now, remember, pressure is specific weight times depth. So that's how to compute. And the pressure at the bottom is greater than that at the top. So it is pressure at the top plus specific weight of which liquid is that, then times the thickness or height of that liquid. So that's all for this lecture series. I hope that this will add to your many problems of experience so that you will become an expert of statics. And I hope that I can be of great help in your preparation, in your studies. And I hope that you understood the lessons I presented here, especially the solution. So if you find some questionable answer, you just comment in the comment section so that I will be able to correct them. So thank you for watching, and please don't forget to subscribe so that I will be uh, encouraged. I will be uh, encouraged to do things about civil engineering topics or even mathematics topics. So, and you will be my inspirations in doing this lecture series. So, thank you and God bless.